Hey, all right, second hour. So, very interesting result here. So, a lot of people would really like the code to be maintainable. As the plane plummets out of the sky, I wouldn't really care whether your code's maintainable. I think I'd rather that the control system in the aircraft was correct. So I'd argue that the really critical thing is if your program's not correct, don't bother. I mean, what's the point? So correctness is critical. It was interesting that maintainable is so high. I thought a few people might have picked reliability because if you take the aircraft example, if something goes wrong, you might want the code to be able to deal with that issue. But yeah, the critical thing is that the program actually works. So correctness, I would argue, is the most important thing. Now I had another idea too. We could run a book here. This is like a horse race, and try and work out which sorting algorithm is going to finish first out of these ones. And anyone who was watching carefully before will know. Any suggestions? There's 4 different versions of bubble sort. Which one? Huh?
How many inputs is strictly that many?
They're all the same. So it's the same number of elements in each array. This column here, the array is sorted in random order, and it looks like the same for all of them. Here we've got one that's nearly sorted to start with, reverse sorted, and one that's got duplicates. So if you want to bet, you've got to choose an algorithm and an initial configuration. Don't know. All right, let's just run it. Although, really, I mean, one thing that you should be doing in this course is, it's easy enough to run it and see which one comes first, but you really ought to be, certainly by the end of this course, be able to reason out which one you expect to come first, and then you're running the experiment simply as a confirmation of that hypothesis. Oh, 2 finished pretty damn quick. Insertion and bubble sort on nearly sorted arrays, almost instantaneous compared to the other ones, but they eventually all finish. Can I redo that? Let's have another look. Yeah. So watch nearly sorted insertion sort and nearly sorted bubble sort. Bang. So both of those go very quick on a nearly sorted array. And the fact that it takes different amounts of time on different kinds of input is interesting as well. If you are considering which algorithm to use, it certainly would help if you knew what kind of input you're going to get. If you know that you're inevitably going to get almost sorted input, then you might want to choose bubble sort or insertion sort out of this range of choices. If you knew that you were getting reversed input, say, then you might want to consider insertion sort as the choice. Now, a lot of the time you don't know what the inputs are going to be, so really all you can do is sort of take an average over all the different possible kinds of input. If you know that certain kinds of input aren't going to occur, then you can discount them as far as consideration for which algorithm to choose. But yeah, there's a lot of stuff to think about. All right, getting back to this sequence thing. Defining pre and post conditions. I think I'll start it. And just a reminder, all of these things end up on the website after the lecture. So I just copy all these files across. They're currently on this laptop. All right, so these are kind of obvious. At the start of this function, we assume all of those things have defined sensible values. What else are we assuming? And it's to do with the relative sizes of relationships between the parameters. So if finish is larger than start, which is possible, then what would we hope about step? Yeah, we'd hope that step is positive if start is less than finish, because then we're going to make progress towards it. So we could describe that. And I get, whoa, this is an interesting one actually. I was going to write less than finish, strictly less than finish, and so that's one possibility. Let's assume that we're not going to have duplicates, although there's nothing in the code to avoid that. And the other possibility is that start is greater than finish, and in which case we want the step to be downwards. So I'm assuming the operator precedence of C, so that OR operation will encompass both of them, but if I want to make it explicit, I can do that. So that's a reasonable step, but now we're making an assumption that start and finish are never equal. So if we wanted to do that, I'll start working from this assumption, and then we'll see how that messes things up in a minute. All right, so the post condition, now this is a little bit tricky because we're not returning a data structure or something, we're writing things to output. So all we can really talk about is the sequence of integer values that's going to be sent to output. And oh, I should have thought about this before I came. Oh no. I can't think of a way to describe it like that. What I was going to say was that I'll have to work this out in a minute. Then the next item is going to be start plus I times step. Okay, so certainly the start value always appears in the output sequence, so we know that the starting point of that's going to be 0. And the end point, I guess, you could simply take that expression there and say, well, that's less than or equal to the finish. So it's a little bit recursive definition, but it'll do for the time being.
For the case where it doesn't equally, the step doesn't equally define the finish.
Yeah.
Would you just describe it by saying, the finish mod step is 0, or
finish?
So you said before there was a.
Oh yeah. I think that this would handle that kind of case as well. Anyway. We're talking about I here. Ooh. Let me cheat. Which I'm allowed to do, because then I can say where I equals, and think about what it should be. So how many times are we going to go through the loop? I would argue, I think, that it's and it's probably going to be what? It has to be an integer, so as written that might be a real number. So it's an integer number of iterations. So two choices, it could either be ceiling or it could be floor. I'm kind of thinking that it might be floor. And I better parenthesize that to make it clear what's going on. So that hopefully will tell us the number of iterations that's going to occur given the start and finish values and the step between the step distance. I may have got that wrong, but I'm sure one of you will tell me once you've had a look at this online. So it's going to be something like that. So we know that the values are always going to be the start value plus a multiple of the step, possibly 0, and the number of times we're going to go through the loop is going to be from 0 up to something like that. All right. So what about some test cases? Now, since we're talking testing, we're allowed to put invalid stuff. So certainly here we can do, 1, 1, 10, that's an obvious case. Go from 1 to 10. Not sure how we're going to engineer that, but oh yeah, we could do that as input arguments. I guess we want to not start at 1 at some point. And of course we want to go in different steps. So 1, 2, 20, we'll overshoot. Let's go 0. And I guess we didn't have any condition on step and finish, start and finish being negative or positive. So in theory, it could be 0. And I guess that would be a useful thing to do. Clearly that one there is not valid input. And I guess counting backwards. So everything's negative, in fact. Let's do something like that. Any other cases that I've missed out? Yeah?
When start and finish are equal.
Yeah. Well spotted. And what would the step be in that case? Probably doesn't matter. All right, let's try that. Good point. That's a very important case. Others? Yeah?
Where the step is greater than the distance between the start and finish?
Yep. Something like that. Yeah. Good point. And I guess you could probably do negative versions of those as well, where the step down is larger than, so -1, -10. Something like that. Anyway, a lot of possibilities. Oh, and I should have been typing all of these into test files. Yep.
I was going to say when step is 0.
Yep. That shouldn't be allowed actually. Ooh, so that's, unless they're the same. Ooh. Alright, so that's another condition that we ought to take account of down here. So if the step 0, what do we expect from start and finish? We expect them to be equal. So that's a sort of unlikely but possible. Does someone else have an idea? Oh, there was another hand there. Nope. All right. So let's see what we can do with this. I have a plan. How do I split this terminal? I know you can split it into two halves. Mac power users, can you tell me? No? Alright, in that case I'll just make another terminal. Haha, that will do.
V split is recommended.
Well, it doesn't matter, this will work. Right, so we can look at those values. So let's see. If you happen to go to the COMP1927 home directory, then you can go further down and you can actually access all the stuff through a path like that. Alright. So, another thing to talk about. So I've got a way of building my program without having to type GCC minus wall minus blah blah error. Did anyone talk about make in 1917? Not really? Good. Alright. So make is a program that reads a make file, and a make file talks about dependencies between bits and pieces of a program. So make is basically a way of taking a program that's constructed of a whole lot of pieces, ensuring that all the pieces are up to date, and then putting them all together to produce the final program. In this case, we've only got one piece. We've got this sequence.c, but in normal programs we'll have a number of different modules that all have to be put together. But let's have a look at a sort of very obvious make file for doing this. So what this make file contains, these are just definitions up the top here, and I'm not actually using them. So I could probably delete them from here just to simplify it. So what a make file consists of a sequence of rules, and associated with each rule there's an action. So this first rule here says that there's a thing called seq that depends on the existence of sequence.o. And when I say depends on the existence, what it's also checking is whether the target is older than the source. So if sequence exists and it's up to date, it's newer than sequence.o, then presumably it was produced from this compilation here, so I don't need to redo the make. So the make file can recognise which actions need to be applied based on the rules. So sequence depends on sequence.o, and to get seq from seq.o, I do this action here. Okay, so this is just the final step in the C compilation. So GCC actually does multiple things. It compiles, which means parsing, producing object code. The other thing it does, it links. So if you've got multiple object files and you need to link them all together, you can do it with a step like this. So if there happened to be something else involved here, so if there were other object files involved, I could mention them there, and if there were other object files involved, I would also need to put them up here. So this thing called seq depends on seq.o, xyz.o, and abc.o. And if any of those .o files are newer than seq, it means they've been changed recently, so I have to reproduce seq by linking all of the .o files together. So you probably should have seen -o at some point. That just says once you've linked everything together, rather than writing it to a.out, write it to this file here. So you're producing seq from those .o files. But of course we don't have xyz.o or abc.o, so it's...
Do you need an output flag on the seq.o line?
This one?
Yeah.
Yeah.
Isn't that going to produce a.out?
No, that's the whole point of -o. -o says write the output to seq.
The next command down. Next
Oh.
command down second.
Oh, okay, yeah, all right. So the next rule says, and make is smart enough to sort of chain its way through the rules. So basically what it says here, all right, should I reproduce or should I make a new version of seek? That depends on seek.o. All right. How do I make seek.o, or where does that come from? Well, it actually comes from seek.c. Okay. So if seek.c is more up to date than seek.o, then I need to recompile seek.c and produce an object file. And this is the C command that will do that. So your question was, how does it know where this is writing the output file to? The default object file that will be produced from a command like this is blah blah blah.o. If I feed in blah blah blah.c, I get out blah blah blah.o. If I really wanted to be explicit about it, yes, I could say, well, not equals. I could say write the output to seek.o, but don't need to do that. And as lazy C programmers, we try to minimise the amount of typing we do, so we don't type stuff that's unnecessary. So, if I modify seek.c, then make is going to look at this make file, say, all right, and the thing it tries to do always is to make the first target that it sees in the file. So whenever I type make, I try to make this thing called seek. And then it says, all right, seek depends on seek.o. Do I need to make seek.o? And then it looks for a rule that has seek.o as a target. It finds it here. To make seek.o, do I need to make seek.o because seek.c is more up to date than seek.o? So if you just modified seek.c, yes, it would realise, yes, I do. So it would do that, make a new seek.o, and then it would do this to produce the final seek command. Most make files will also have something to clean up a bit, and you can see that here we've got a target called clean. We don't actually create something called clean, and because we're not creating anything, we also don't have to say where it comes from. So if you put a target there without saying what the sources are, it will always make that target. Yep.
In this particular case, I'm just curious, because is this, like that, the two-step process there, is that actually necessary? Or
No.
Could you just do the
Yeah. Yeah, you could have done what you normally do, but 99% of make files aren't going to be as simple as that. They'll have multiple object files involved, so you'll need to do more. All right, so let's see how that works. Oh, right, so that was the very simple version of the make file. Here's one that's in some ways simpler and in some ways more complex. And I should get rid of that because we don't need it. So you can specify, so make understands various aspects of Unix or Linux. It understands how to make a .o file from a .c file. And the way it does it is by saying, all right, I'm going to run whatever C compiler you've told me about, and I'm going to use these flags when I run it. Okay, so here, I don't actually have to specify the action. Make can work out the action, and it's going to use these values here. So to create seek from seek.o, it realises, okay, I'm creating a binary from a bunch of object files, so I'll just link them all together. And if you've got a .o file being dependent on a .c file, it knows how to make a .o file from the corresponding .c file, so it can do it. Here we've got our clean statement again that simply removes the .o file. -f basically says, don't complain if the .o file doesn't exist. Otherwise it'll whinge and say unknown file or non-existent file. And vclean means very clean, and it not only gets rid of the .o file, it also gets rid of the final executable file. So let's see what happens if we use that. So at the moment, what have I got in my directory? I've actually got a .o and I've got a seek. So if I try to make it, it'll tell me seek is up to date. And I could check that by actually looking at the timestamps on all the files. So you can see that seek is more recent than seek.o. Seek.o is more recent than seek.c. the other thing it'll do, if the file doesn't exist, then it will definitely try to create it. If it doesn't exist already, it will try to create it. So if I was to actually just remove the seek binary, I can then run make, and it will say, oh, there is no seek, so I'll have to apply the rule to create seek, and it will do that. Notice that there are no flags involved in the linking step, because you've really done all the error checking that you need to do in the original compilation. Right, so if I do make very clean, that will get rid of the .o file and the seek file, and then if I tell make run it again, the first thing it'll do, it'll run GCC on seek.c, and there it is using the -o. And it's also using the C flags that I specified. Okay? And then, having created seek.o, it will then use seek.o to create seek. Right? So having a makefile set up with all these dependencies in it makes it really easy to rebuild stuff. You don't have to either use the up arrow to go back to the previous compile file, or type a whole lot of long compilation steps in to the terminal. You just type in make, and it knows what to remake. This is really useful when you've got a very large collection of files that are all being combined to make a single executable. Alright, so that's a very brief introduction to make. Anyway, so what we're meant to be doing is looking at seek. So there's an example. Seek will count from 1 to 10. It will also count from 3 to 5. It will also work its way backwards. If I say the finishing point is -5, then if you only specify a finish point, it always starts counting from 1. Okay? What else? Oh yeah, counting with steps. Alright, let's try some of these examples over here. Yep. Oh, damn. What did I do there? I could have sworn. I thought I trying to be too smart. Alright, let's just... Oh, I'm just grabbing everything. Okay, so that's doing the right thing as well. The start point is -1, going down in steps of -10, the end point is -5. It's obviously just going to print -1. Alright, so you saw my complete debacle of an effort to try and copy and paste the test cases. It might be nice if we could somehow package these test cases up in a way that would be easy to run them each time. And so that's the second thing I wanted to show you, is setting up a test suite. So here we've got a directory which contains test cases. If we look at one of these test cases, we can see that it's actually a command to execute the seek program and produce some results. Now, if we want to check whether the test has executed successfully, we need to know, and this applies all the time, we need to know what the expected output is. So, if we don't know what we're expecting, well, we can run the program and just get random stuff and say, well, that might be right, it might not be right. We need to know what the expected output is. So that's what we're expecting to come out of that. And you can build up a whole collection of test cases, and I'm trying to think of a nice way to turn all these into test cases, but I can't. So I might just put in a few more of these. So let's try that, say. Right, so what are we expecting with sequence 5120? The expected output won't be just 2, it'll be 5 to 20, counting in steps of 1, 5, 6, 7, 8, 9, 10. Now I could have done this much easier because there's already a command to do this, and I could have just used that to generate the expected output, but in the general case you're not going to have a command that can generate the expected output already. Alright, so if I were to run one of these tests, let's say I want to run test 01. So test 01 is a command. I can run that command by piping or by sending it into the shell, and the shell will cause that command to be executed, and I'll get that result. Okay. Now what I want to do, of course, is I want to compare that result to the expected output. So I'll need to capture that result in a file. So what I could do is say, let's put that in an observed file, and then I want to compare the observed output to the expected output, and Unix has a command to do that called diff. So there's my observed, there's my expected, and I run that and I see nothing. And that's good, because there shouldn't be any difference between the observed output and the expected output if the program is correct. Okay. Let me just fiddle with the observed output and show what happens if the output isn't correct. Let's say I had a one-off error and it didn't produce the last one. Then I do that diff, and diff produces output in maybe a slightly weird format. Basically what it tells you is what's different between these two files. And it's saying to get from observed to expected, I'd need to add an extra line containing the value 10. So after the line 9 in the observed output, if I add a line containing 10, then I'll get the expected result. Okay, so sometimes it's a little bit hard to interpret the diff output, but basically really what we're interested in here is, are the outputs the same? So as long as nothing comes out, we're happy. All right? Now typing these long commands is a bit tedious, so what I've decided to do is to set up a little shell script that will check all this stuff for me. So let me see. All right, so first thing, in the remote chance that we have an infinite loop, this ulimit thing here will only allow a program to run for 1 second, and that should be plenty of time for any sort of moderate test case. You can generate a hell of a lot of output in 1 second though if we do have an infinite loop. All right, then we've got this for statement which basically says, look at all of the tests. Let me just comment this stuff out. So if I was to run this, all it's doing, it's looking in the tests directory and it's seeing, do I have test files called test something something, test something something. Any file that looks like that, it will pick that up and use it as a test case. So you can see it's picked those two up. So ls, okay, you know the ls command gives you a list of files in a directory. You can specify a pattern, so it will only give you a list of files that match that pattern. So what I'm saying is, anything in the test directory where the file name only has 2 characters in it. So 01 and 02. So I'm making some assumptions about what the names of my test files are going to be. Right, so it'll pick up all those test files one at a time, and then for each of them it will execute the test using the shell. So shell with test.01, you saw me do that before. Ultimately it redirects the output into test01.observed, and just in case we generate a large amount of output in our 1 second of execution time, I'm going to chop off just the first 100. Okay, that's just for safety, so I don't generate megabyte size files on the off chance I've got a infinite loop. And then it runs the diff command. Okay, so if I execute this, it's going to look at each of the test cases in turn and run them, and we're going to get output that's remarkably like what we saw above. Okay, so the fact that we've got no output after each test line tells us that the observed output was the same as the expected output, so we're happy. If you really wanted to make it clear that everything was okay, you could always check whether the output is empty, and then if it's empty, print OK. If it's not empty, print not OK, or something like that. That's a little bit more fiddling around in the shell. So that was about as simple as I wanted to get. So let's try a couple more of these test cases. Here's one with all negative numbers. So I don't need to tell the check script about new cases, it will just find them. As long as I put them in a file called 01, 02, 03, whatever, it'll discover them and use them. And of course we need some expected output. And let me just try. Cool. So the built-in sequence command can generate my expected output for me. It actually generates the correct output, which is good. And then of course you might say, why are you bothering to write a sequence command if one already exists? That's true, but it's an exercise, you know. Just because there's a cat command doesn't mean we won't ask you to write one. Let's see, let's pick this one. Alright, I've got to type that in myself. I should have known that. It was only going to be one line. Anyway, so now I've got 4 test cases and I can try checking them. Run the script again. It's going to run each of those test cases. Ooh, what's that? To command not found. Oh, what did I do wrong? I know what I did wrong. Why didn't someone pick me up on it before? It has to be a complete command. Okay, anyway, that's interesting because you can see one of the tests screwed up. It didn't screw up for the right reason. It screwed up for the test being invalid. Ooh, what's all this then? So, test 1, okay, there's no funny output. Test 2, okay, no funny output. Test 3, okay, no funny output. Test 4, what's the story? Alright, so looking at the output, so this is the diff output. It's saying that I can make the expected look like the observed if I add all these numbers on the end of the expected file. So the expected file should have just had the value 2. What actually comes out is a whole lot of other numbers. And if you look really carefully, it stops at 101. So if I actually ran it from here and type the name correctly, it would do that. Oops. We're not going to stop in a hurry. Right, so that's a screw up. If the start and finish are the same, the command goes into an infinite loop. I'll let you debug that because we're getting close to the end of the lecture. And I didn't get nearly as far as I intended. All right, any questions on make, all that check stuff? All these scripts will be there attached to the course website, so you can go and have a look at them and try and work out what on earth's going on. Generally, we'll provide you with these kind of check scripts. Maybe we'll ask you to write some test cases. All right.